very much. It's lovely to see many old friends and some new faces. And so like I was telling Marcos, I'm only sad that I can't be in person giving this talk. So maybe hopefully soon the world would be better and I could come in person. But in any case, yeah. So everything I'll talk about today is joint work with Chao Li. And so I think many people are experts in minimal surfaces here. I have the impression. So I'll give a very brief introduction, but I think the talk may be slightly on the technical side, which means that you should definitely interrupt me in case something doesn't make sense, right? So I want to give some idea of the details, but that's useless if no one understands what I'm saying. So please interrupt me, endlessly, etc. Okay. So as everyone knows, right, a minimal surface is a critical point of the area functional. So equivalently, the mean curvature is 0, and here are two very nice examples of minimal surfaces known for many, many years. And so one of the great and beautiful theorems about minimal surfaces from quite a long time ago. Now it's over 100 years ago, I guess. That's incredible. And so that says that if you have a minimal surface in R3, which is the graph, oh, I guess I can draw. What am I doing? Okay, so here's R2. And so you have some surface, which is graphical. This is graph of some function of U, right? And so Bernstein proved that in this situation, if the graph is entire, so the domain of the graph should be all of R2, then actually this graph should be a flat plane, right? So this is quite an amazing theorem. And you can think of this sort of like a nonlinear Liouville type theorem, right? So the minimal surface equation is sort of like the Laplacian. And here you see that an entire minimal surface is a graph, or is a flat plane. Okay, and so probably many of you know this story very well, but this was a huge, this occupied geometric analysts for quite some time, until really the 60s, the question of Bernstein's theorem in higher dimensions. So, okay, in R3, you have a graph, but what about in R4? And so here I should really add, this is for hypersurfaces. Right, so U is scalar valued. Okay, and so, for example, two-dimensional graphs in R4 is much more complicated, and I'm never going to talk about higher codimension today. Right? So probably some of you know a bit about that story, and if you do, you know why I won't say anything. So we're always going to consider hypersurfaces. Okay, and so the main points I want to take away, right? So if you are not too familiar with this, the main points I want to say is, first of all, if you have a graph, then it minimizes area. Okay, so a minimal graph actually is a minimum of the functional, right? This is quite surprising because minimal just means a critical point. Oh, sorry. Right, so here you actually can show that a critical point is a global minimum, right? You should never tell this to your calculus students, but in this special case, the thing that they probably mess up all the time is actually true. And then any area minimizing surface is stable. Okay, and so this is just kind of my warm up to talk about the topics that we're going to discuss today. And so stable means that the second derivative of area is non-negative for all variations, and here I mean compactly supported. Okay, so a surface is going to be stable, right? So it's minimal if you vary it on a compact set and the area doesn't change to first order. And then it's stable if it only increases or doesn't go down to second order. Okay. All right. So you see that, right? If you first start studying minimal graphs, which is the classical thing to do, right? Then maybe you're led to the study of area minimizers, which is more general, right? Or even you might move from area minimizers to stable, right? So that's kind of how the field has progressed. So first, people studied minimal graphs. Then there was actually the theory that was developed around minimal graphs was equally well applicable to area minimizers. And then people started trying to generalize from area minimizing to stable. Okay, so if you remember, we said that a minimal graph is a flat plane, at least in sufficiently low dimensions, right? And so the following terminology, I don't know if this is widely used, but many people I know would use this terminology. And so we can ask about the stable Bernstein problem. So the Bernstein problem is a minimal graph, a flat plane, and the stable Bernstein problem replaces minimal graph with stable. Okay. All right. So you might call this the stable Bernstein problem. Okay. So let me just make sure we are okay with the terms. So two-sided means that there's a continuous unit normal. Okay. Stable means the second variation. It's not negative. Minimal means, well, this should come first. Right? Hypersurface, obviously, and flat plane. Okay. Is that all right? All right. Okay. And so it's well known by now. This is, in modern terminology, this is obvious, but this was I think this is a big idea. But this question is the same thing as asking if any stable minimal hypersurface in a Riemannian manifold has curvature estimates, right? So it's when I say curvature estimates, we won't really talk about this too much, but the second fundamental form is bounded by some constant. Okay, this is not exactly. I mean, if you like, you should to make this equivalence precise, you should state it in a very precise way. I won't do that, but morally, the stable Bernstein problem is the same thing as asking about bound if there's a sort of a priori bound on curvature for stable minimal surfaces. And okay, so I just want to give some indication about why you might care. I mean, I'm not going to have time to go into this, but why you might care about stability as opposed to area minimizing, right? So remember, area minimizing implies stability. So proving estimates for something stable is a generalization of the study of area minimizers. And so I think many people here have used estimates for stable minimal surfaces. And let me just tell you kind of some places they come up. And so the first and maybe most fundamental place that stability arises is when you're studying min-max problems. So particularly like Omgren-Pitts theory. So you can prove, it's not obvious, but you can prove in the setting of Omgren-Pitts theory that min-max hypersurfaces locally look stable in a certain sense. But you don't know if they're area minimizing locally. You only know stability. And so you need to prove curvature estimates for stable surfaces to work with that theory. And similarly, once you know about min-max produces lots of minimal surfaces. I think we've seen that that playing out over the last 10 years, right? 10 years. And so then you ask about compactness. Once you have many, many surfaces, you can ask if they have compactness properties. And so if you try to look at those surfaces, the natural property of those surfaces that you have is a bound on their Morse index. And a bound on the Morse index is like having locally stable. Okay, so again, and you don't know anything about the area minimizing property. There's some other situations. So if you're studying minimal laminations, again, in certain situations you can prove that some leaves are stable, and you want to understand that, and you don't have an area minimizing property. And also one thing I quite like is if you have M1, M2. So if you have two disjoint minimal surfaces, any minimal hypersurfaces, say. So a classic thing to do is you should minimize area in between. Right, so these act as barriers for the minimization problem. So you can put a minimizer in between. And this is a minimizer, but it's not a minimizer with respect to all competitors, right? You can't draw this competitor. Okay. And so, well, that causes some problems for certain estimates for minimizers, but the red thing is definitely stable. So if you understand stable things, you definitely understand the situation. Okay. So are there any questions about this? This is just, you can forget about this. This was just kind of trying to justify the study of stable surfaces. Okay. Okay, so the theorem, which I think is very well known, is the following. So this is from maybe late 70s, and so three different groups I think are usually credited with this result. And so this is the stable version of the Bernstein problem in R3. So instead of a minimal graph, you just ask that it's stable. So remember, minimal graphs are stable, but we don't want to assume that it's a graph. We just want to look at a stable minimal immersion. And indeed, you get that it's flat. Okay, and so the first two proofs are sort of similar. So by Fisher, Colbert, and Shane, and Docamo and Peng are more or less similar. In some technical details, they're different. The Pogarelov proof is a bit different. That's kind of an interesting alternative way of thinking about this. But I'm not going to talk too much about the proofs. But just sort of, so this is sort of the result, which the result along these lines that is quite well known. And so Antonio Ross showed not that long ago, actually, that you can drop the two-sidedness assumption. I really love that. That's quite a paper that I quite like, but I won't talk about anymore. From now on, everything is two-sided. So the Ross's paper is quite cool, but we don't have time to discuss that more. Okay. And so this is kind of not quite the end of the story, but there's not too many more results along these lines. There's some quite famous results, but there's not that. The list is short. Okay, so what I want to talk about is basically the stable Bernstein problem in higher dimensions, right? And so this always hypersurfaces. Okay, so you consider an immersed, two-sided, complete, stable minimal hypersurface. So complete just means that the induced metric is complete. Okay, so this already, you can already find non-flat area minimizers in R8. This is a very famous result. And so you definitely know that the stable Bernstein problem, well, it's not true that stable minimal surfaces in R8, hypersurfaces in R8 are planes anymore. So okay, there's probably many interesting questions you can ask there, but you can't have such a simple answer once you get to R8, right? And so then the next result is a positive result, which says that in R6 and below, if you assume that the area growth is Euclidean, right? So sigma is n-dimensional. You assume that the area grows in the Euclidean manner, then it's flat. So this is proven by Shane, Simon, Yao. And then in higher dimensions, you can say some things that are like this. And I won't, if you don't know what this is, it's hard to say. And if you do know, you already know. So Shane, Simon, and Wickramasekara have some related results in higher dimensions in particular. But all right, we're just going to ignore that here. Okay. And so these, I think, these two things are really the well-known results. And the other two are quite well-known, but maybe not as well-known. And so Shane Yao, a few years later, proved that if you suppose you have a complete stable minimal immersion in Rn+1, and this works in any dimension, and suppose you have a harmonic function whose gradient is an L2, right? So this is like finite Dirichlet energy, right? Then actually this function is constant. Okay, so on Rn you can prove this integration by parts, say, right? So but it also holds in a stable minimal surface. And so about 20 years later, Kaushen and Zhu proved that using this Shane Yao result, that a stable minimal hypersurface has only one end, right? So this, okay, if you don't know what an end is, it's a little annoying to define, but you know it when you see it, right? Because this has two ends, right? So this picture is ruled out. Okay, and so, well, the proof, at least if I don't tell you the details, is very easy. The proof is if in this picture I put 1 here, I put 0 here, I minimize the Dirichlet energy inside. I get some harmonic function, right? And then, well, I can let these things go to infinity, right? And then I should hope to get a harmonic function. Of course, the difficulty is to prove that harmonic function is not constant and get a contradiction from number 3. But here you should use the Michael-Simon-Sobolev inequality. Okay, so there's on a minimal surface in Rn, there's a Sobolev inequality, and that prevents this function from becoming constant in the limit. Okay. All right. So that's not, I mean, it's not a direct, it's not direct, you have to make some argument, but you can do that. Great. Are there questions otherwise? Any questions? You guys are quiet. You guys are quiet.
Can I have topology?
Sure. Yeah. It's nothing is known. So the only thing you can say, and I'm going to use this in a minute. So if sigma n is Rn plus 1, this is a stable minimal two-sided, right? Then you can prove, I've drawn this in a funny way, that any cover is such a thing, right? So you can lift. So if you're a two-sided stable minimal hypersurface, you can always lift to a cover, right? And so you could assume that pi, and I'm going to do this in a minute, right? So you can assume that pi 1 is 0, right? And number 4 says that you have one end. Okay, but there's many non-compact manifolds with pi 1 0 and one end, right? So in general, it's totally unclear if you could have topology. And I think, now that I'm recorded, I'm nervous to say this, but I think it's probably unclear if there exist. Yeah, okay. Let me just say, off the top of my head, I'm a bit unsure what you can say about the topology in these non-flat examples. Okay, so it would be interesting to say what those two. I think you could say this explicitly because they're sort of explicit. So
okay, thank you very much.
Yeah. Thanks for the question. So yeah, you should imagine that you don't know exactly. I mean, if in higher dimensions, you don't really know what sigma should look like, right? If you're not in one of these cases where we do know. Other questions? Thanks a lot for the question. Okay, so what I'd like to talk about today is the following result that I proved with Chao Li. And so this is the analog of the Fischer-Kolber-Shane, de Cramal-Peng, and Pogorelov result in one dimension higher. Okay, so only modest progress, right? We're not going all the way up, but just one more dimension. And so this is for a 3-manifold immersed in R4 as a two-sided complete stable immersion, then you're flat. Okay, and so just to remind you that Shane, Simon, Yao say that if the growth, if a coordinate ball, let's say intrinsic, you could also say this extrinsic, this is O of R3, then you're flat. So Shane, Simon, Yao tell you that if you grow in a controlled manner, I mean, you could actually you could make up a slightly better exponent there if you really wanted. So if you grow in a controlled manner, then you're flat, right? So this question is really going to be about some sort of sigma, which becomes very complicated near infinity. So that's the picture you should have in mind when you think of this. So like, I don't know. So somehow sigma is wrapping around more and more times as you go out. Although I think that picture is completely incomprehensible. So so this, just to set the stage, this is the thing you should have in mind that we're trying to rule out. And so just to be clear, we are not going to reduce the theorem to this Shane, Simon, Yao, although we will use the work of Shane, Simon, Yao. I'll explain that later. Okay. So I don't want to go into the consequences beyond just this slide, but there are some nice consequences of this estimate. So first of all, you get like area, you get curvature estimates, like I said in the beginning, for stable minimal hypersurfaces in a 4-manifold, and they don't depend on the volume of the surface. Okay, and so Shane, Simon, Yao give you estimates that depend on how much area there is in a small ball. Okay, so you show the constant doesn't depend on the area, and I think that will be useful for if you want to study bounded index hypersurfaces in a 4-manifold. You could say some things that were only known in a 3-manifold before, for example. And then something which is quite dear to my heart is Fischer-Kolbe proved a really nice result. I haven't defined Morse index, but if you know what that means, so like finite Morse index is equivalent to finite total curvature for a minimal surface in R3. Okay, and so here this shows that can be extended to R4. So you have second fundamental form in L3 if and only if you have finite Morse index. Right, and so this was previously known, again, if you assume that the area grows in a Euclidean manner. But now it's now known in general in R4. And so, using this, for example, you can try to relate the index to the topology. So work of Chao, maybe the first paper he wrote in grad school, I think, is considering the 4-dimensional case. It's quite a nice paper. Davi Massimo and I have some 3-dimensional work, generalizing work of Ross. And so but I'll just remark, like, okay, so I really like the following problem. So you might ask if an index 1 hypersurface in R4 is the 3-dimensional catenoid. So usually you think of the catenoid in R3, but you can also equally well find a rotationally symmetric catenoid in R4. It's a bit different because it's bounded between 2 planes. It has the bounded height, but okay. It has index 1, you can prove that, but it's not known if that's a unique index 1 surface. And I mean, I think this is kind of an important question if you're interested in compactness of index 1 surfaces, which come naturally from min-max. So that's quite a nice problem. I don't know. I'm not sure if there's much hope to solve it or not, but it's a nice problem. Okay. Okay, so yeah, in my remaining time, I'd like to discuss the proof. So again, it's somewhat technical, so please interrupt me if you forget some definition that's or whatever. It's hard with the slides to keep remembering what everything means. Okay. So so I want to start with the basic reductions. And so we're going to assume you have some 2-sided complete stable minimum immersions, and I want to make some reductions to the problem. And some of them are quite, these reductions are quite crucial, but I'll try to explain why later. Okay. So first of all, I want to assume the curvature is bounded. Okay, so this seems funny because, well, how can I just make this assumption, right? Here, well, if the curvature goes to infinity, you could pick a good sequence of points, rush off to infinity, like bring those points back to the origin, rescale, zoom in, so the curvature becomes 1, and take the limit, and then you actually get such a surface, right? And so this is kind of a well-known sort of point-picking argument. Okay, so it's a bit funny that you are allowed to do this, but you are. I'm not. It's somewhat strange, but okay. So what we say is that if there exists a non-flat thing, then you can assume that there's a non-flat thing with bounded curvature. Okay. So the second step is, I explained this already a little bit, or I at least asserted this already, is that stability lifts to any cover. So this is very important. And so we're going to lift to the universal cover. And so, okay, and it only has one end. I should have probably said this. Okay. Oh, I see. Yeah, this is okay. So then the next, okay, so the next fact, so we have only one end and we have bounded curvature. We don't know if there's some topology, but at least you're simply connected. I don't know how to draw something non-simply connected, or something simply connected, but with funny topology. Okay, here's sigma. And so then the next fact, it turned out to be well known, although I didn't know this when I started this project. So a stable minimal immersion into R4 or in Rn hypersurface is non-parabolic. Okay, so before I started this project, I could never remember which is parabolic and which is non-parabolic. But now I know non-parabolic means that it exists a positive Green's function on the manifold. Okay? And so it turns out that using the stability inequality, you can construct the positive Green's function on any stable minimal surface, because essentially the thing, when you're constructing a Green's function, you can always find Green's functions on compact domains, and you need to take the limit as the domain exhausts the thing. And the thing that you're worried about is the Green's function becomes sort of trivial. Like it becomes limits, these things limit to 1. But actually you see that if this is happening, this is the ultimate test function to plug into stability, because it's a function with small Dirichlet energy that limits to 1. So it's like the log cutoff trick in R2. So then you just immediately conclude you're flat and you're done, right? So, you can see our paper, but there's also many places that discuss this. So there exists a Green's function. And moreover, this is the next fact is very important for us. So if you look, so I'm going to call U throughout the rest of the talk. U is going to be the Green's function. I don't know, maybe that's not a good choice, but okay. And so then I want to define gamma sub S to be the S level set of the Green's function. Right? So gamma sub S is a two-dimensional thing inside of sigma 3, which is immersed into R4. Okay. Okay. And so as long as S is a regular value of the Green's function, this gamma sub S is going to be compact and connected. And both of these facts are crucial. Okay. And so the connectedness, I can even sketch the picture. So suppose that gamma S was not connected. Okay? You have these two sets. Then, well, okay, you only have one end, right? So we've arranged only one end. So in this picture, one of these two sets has to close up, right? If they were both open, then you have two ends. You sort of split. Okay, so you split here. Okay, but now, right? If you look at this, like at this region, you know, depending on how you're choosing things, gamma S either has a minimum or a maximum inside because it's cut. You've cut by U equals S. So then the maximum principle gives you a contradiction, right? So that already tells you that you have to have exactly one component. Okay. Again, you don't know what the topology of gamma S is. It could have higher genus, could change topology as you go out. We don't know, but that's the general strategy, or that's the general picture. And so let me sort of erase this so we can see this. And so just to have in mind the strategy for the remainder of the proof is I want to use, so okay, in R3, the Green's function is like R to the minus 1. Okay, that's very important to keep in mind. So if you're R3, the Green's function looks like this. Okay, so in R3, the coordinate R is very useful in many things, right? You want to do some radial cutoff test function type thing. So you could imagine that if you know U, that's good enough. That's the same thing as knowing R. Okay, you changed coordinates, but we know how to do that. Right? So that's not so worrisome. And so the idea is that the function U will replace the coordinate R, right? So you should always think of the function U as being it's not a full coordinate system, but at least it's like one nice coordinate on our manifold. Okay. And so that's the first thing I should say. And the second thing I should say is that I feel very justified because I was the first time, from the beginning of Chao and I trying to solve this problem, I was saying that this is a problem about scalar curvature. Okay. And so I think indeed this was correct. And so you should really think of this as a problem about scalar curvature. And so what does that mean? So you'll sort of see how that comes in. But so let me just give you some intuition, right? So Shane Yao say that if you have a stable minimal surface in positive scalar curvature, then you can do a conformal change on the induced metric to make the minimal surface have a positive scalar curvature again, right? This is what maybe you call conformal descent. So this is how they prove that N torus doesn't admit positive scalar curvature. And so, so somehow you should think of the minimal surface as having positive scalar curvature. It doesn't. It definitely does not have positive scalar curvature. That's completely wrong. And the other thing is we will never actually conformally change the metric. You don't actually want to do that, but that's what you want to think in your heart. You're looking at the PSC metric. Okay, so these two things are very important to keep in mind. So we're going to use two tools, and both of those tools are going to come from the study of PSC manifolds, positive scalar curvature manifolds, right? So but I'll just remark that the scalar curvature of sigma by the Gauss equations is actually, so we'll use this later, but right, the scalar curvature is actually non-positive, right? So this is quite confusing, but the stability inequality is somehow telling you that it's positive in a certain sense, right? That's the way you should think about it. Okay, all right. So maybe that makes no sense, but if in case there's a question. I'm glad to take stuff. Cool. Okay, so in order to explain the proof, I need to tell you, I guess, two things that basically have come up in the study of scalar curvature, like I said, in very recently, actually. And so let's just sort of pause for a second to consider a three-manifold, just arbitrary. I mean, in applications, it's going to be sigma, the minimal surface with the induced metric. And suppose you have a harmonic function on sigma. Okay, so I think everyone knows the Bochner formula, right? This is probably you first learned this in your first class on Riemannian geometry. And this tells you that the Laplacian of the gradient of the harmonic function, well, you can try to commute the derivatives. You get a curvature term, right? Because it's harmonic, once you move the Laplacian inside, you get 0. So then the thing you get is Ricci curvature. Okay. So this is a famous theorem. And this is the thing that Shane and Yao used to say that, just remarks, as Shane Yao say that Laplacian U is 0, grad U is in L2. Implies U is constant. And they basically are going to combine this Bochner formula with the stability inequality, right? So they're going to plug something that looks like, I haven't said what the stability inequality is, but if you know, into the stability. So they're going to use this, and then you integrate by parts, you recover a Laplacian of grad U squared, and then you go from there. And so the basic idea that we're going to use is very simple, given the following really nice observation of Daniel Stern just a couple years ago. And so Daniel Stern observed that, well, you can take the Bochner formula, and remember that I said this is a problem about scalar curvature, right? So Ricci curvature is too complicated, so we would like to instead consider scalar curvature somehow. And so let me, okay. So if you consider the two-dimensional surface, the level set of U, just for a general harmonic function, but later it's going to be the Green's function, then the normal vector, or one normal vector, is grad U over norm grad U. Okay. So this term is basically Ricci of nu. Okay. And so if you're familiar with the Shane-Yao rearrangement of the stability inequality, right? Okay, if not, it's easier for me to just tell you what's going to happen. You can apply the Shane-Yao rearrangement idea to turn this into an ambient scalar curvature term, a Gaussian curvature, the second fundamental form, and a mean curvature terms. Okay, so if I try to get the signs, I'll mess it up. Okay. But there's some, you can express that in terms of this. But the amazing idea then of Dan is that these two terms, if you have a level set of a function and you try to express the second fundamental form and the mean curvature, this is a great exercise in Riemannian geometry. It's basically the second fundamental form is basically the Hessian, right? Up to a factor. Okay, so but the Hessian already arose in the Bochner formula, right? So okay, you have to do the calculations to get it all worked out. But when you do that, you get the following version of the Bochner formula. Okay, so the Ricci curvature term turns into the ambient scalar curvature, so we're very happy. There's a Gaussian curvature term. That's also very good. So that's the Gaussian curvature of the level set. And the trade you make, this is an excellent formula. So you lose a bit of the Hessian. So the Hessian is a good term, but actually you gain a bit of this Kato type term, if you know what that means, right? So the second term is kind of like the Hessian. It's not quite as big as the Hessian, but you gain a lot of it. So if you just add if you add the powers, you get 3 halves here instead of 1. Right? So that's great. Okay. So I've just deleted the original Bochner formula. And so now, right, if you expand the square here, then, well, you get this term, the 2 gets canceled, and then you also delete this term, right? Because that's the cross term in the Laplacian. Okay. So notice that we ate this term, but then we kept this remaining Hessian term, right? So that's very nice. Okay. Actually, for applications, it won't matter that if you got 0 here, it would be okay, I think. But okay. So here's what you end up with. And so Dan Stern had this really cool idea, which is you start with this version of the Bochner formula. And you should, let's say you just had a harmonic function on a compact manifold. That doesn't really make sense, but okay, don't worry about that. So if you integrated this, you should use the coarea formula, which says the following. So if you integrate over your manifold, grad u times a function, that's the same as changing coordinate using u as the coordinate. So you integrate over the level sets of u, just the function, right? So this is the area factor, right? That's a nice. You can draw the picture that convinces you of that, I think. Right? So, okay. And so notice that the way I've written it is awesome, because here, this goes away under the coarea, right? So if you try to integrate this formula, you're going to end up with the integral of k gamma s, right? And as we know, one of the greatest theorems of geometry tells you that this is 2 pi chi, right? So Gauss-Bonnet. 4 pi chi? No, 2 pi chi. I always mess up the number there. Okay. Now that that's recorded, that's embarrassing. So Dan uses this to give a proof of no positive scalar curvature on T3. So this was originally proven by Shane Yao and Grobov-Lawson. But Dan's proof is very simple, I think, compared to those two proofs. It's an interesting open question if you can use such a proof in T4. Right, so that's open. And I think that would be the first step of trying to extend the work of Chao and myself to higher dimensions. So you would definitely need to understand Dan's proof on T4, which so far I think many people have tried, and I've tried, and I know Dan has tried. And so it seems tricky, although I think with the right point of view, maybe it's not tricky, but it's unclear. Okay, so great. Okay, so this is the first step. And so we have this nice Bochner formula. And if you remember, I said this out loud, but I didn't explain this. But what Shane and Yao do in their harmonic function paper, they work with harmonic maps, but for harmonic functions, they plug in the thing that gives you the Bochner formula. And you plug in grad u to the first power in their paper. You integrate by parts, use the Bochner formula in stability. Okay, so I should have said this earlier maybe, but if you're stable, you can compute. That's the same thing as this sort of inequality for all compactly supported functions. Okay, and so if we want to use the Stern-Bochner formula instead of the Shane Yao, you read the Shane Yao paper, they use the Bochner formula. You have this idea. The idea is not very hard, which is you should try to use the Stern formula instead of the Shane Yao formula. See what you get. Okay, and so you quickly see that you have to choose this power of grad u because you want to use coarea formula and Gauss-Bonnet. So this might seem strange, but like when you say I want to combine Stern and the Shane Yao strategy of stability, you can only use this power of grad u because you need to use the coarea formula. Like you cannot integrate grad u k, right, over gamma s. This is completely unknown, so you have to just get k. So okay, you try it with an arbitrary power, you quickly see that this one is the only one that works. Okay, and so as usual, right, this function is not compactly supported, so you need to take a cutoff function to make it compactly supported. And so you should cut off away from because we're using the Green's function, so you have to cut off away from the pole and infinity. Okay? And so the second idea, which I think is not so hard in retrospect, but it was kind of an important jump, is that your cutoff function should be defined again in terms of u. Right? So you should imagine that the cutoff function looks something, I mean, we'll make precise what it is later. It's phi of u. And so you need to cut off, you should imagine trying to do something like this, right? So you cut off near 0 and infinity, right? So then this is a nice allowable test function. Okay, so I'm not going to do this calculation because nobody wants to see me do that at this time of day. And so, but I'll just tell you what you get. So what you get is the following. So on the left-hand side, you should imagine that you get some piece of this left over. And what you get is the integral over the level sets of the ambient second fundamental form squared. Okay, right? And this is always times phi of s squared, right? We've used the co-area formula here. Okay. So this term is coming from Gauss-Bonnet. Okay, and so 8 pi over 3, you can imagine, is some multiple of 4 pi, right? And so here we use the fact that level sets are connected to bound the Euler characteristic by 2. Okay, so that was the reduction I did there. And this term is somehow the Dirichlet energy. Okay, and so you get the derivative of the cutoff times the integral over the level set of grad u squared. Okay, so the exact form of this inequality is actually quite important, but there's no need to remember it. But the exact form is very important, and this constant here is really important. Okay, so like really, you derive this inequality. There was a 4/3 on the left-hand side. Like you lose a bit here, you lose a fourth here in some sense, but then I just put it over on the right-hand side. Okay, so we'll come back to this later, but. So, okay, what I want you to take away at this point, though, is that this term is basically telling you what kind of phi you can plug in, right? This is always the game. You have some inequality, you get a phi on, you get a cutoff function on the right-hand side, and you need to choose a good cutoff function. And so, well, okay, we got to here, and you start saying like, okay, you start playing the game of what can you do, but you realize that this thing that I'm going to call f of s is very, very important. Okay. The behavior of f of s as s goes to 0 is telling you what kind of cutoff functions you can plug in, right? S going to 0 is the difficult part because you go to 0, that means you go to the end of the manifold. That's where we don't know anything there, right? It's winding around. It's very complicated, right? So, okay. So s goes to 0, you need to understand f of s. Okay. Okay. Are there questions? Okay. So, okay, so, right, I mean, what is f of s? I don't know, it's not clear at all to start. So on R3, and this is very important to keep in mind, if you're bored, you can just compute this, right? So take on R3, right, u is 4 pi r to the minus 1, and you can, in 2 minutes, you can compute that f of s is 4 pi s squared. Okay, so this is important. The s squared will be important. Okay, but we're not on R3, right? The manifold is very complicated. So then you start asking, like, what's the best a priori bound? What can you start with, right? How do you have to get your foot in the door before you can prove anything, right? So the trick is the following. So for the first observation, remember I assume that sigma has bounded curvature. This was my point picking argument at the beginning. And so, right, Yao has differential Harnack that tells you, right, so like as long as you're far away from the pole, you can bound u as a positive harmonic function on a big ball. So you can bound grad log u by a pointwise constant. Okay, right? So that's the differential Harnack, right? Usually, to get the usual Harnack, you integrate that over a curve, and you get that u doesn't move very too much. Okay, but for us, we need the differential version. Okay, so now we can write grad u squared. Well, let me turn this as grad u. Okay, and let me give up one of them. So let me give up this c times u, but this is over gamma s, and u equals s on gamma s. So we get s integral of grad u over gamma s. Okay, but now the funny thing is that this is o of 1. It's actually constant because you can easily see that. Oh, that's not quite right. Okay, so if this is gamma s, then remember the normal vector is grad u over norm grad u. So integral grad u of gamma s is integral of grad u dot nu. Right? You check the power. You always get confused here, right? But you check the powers. Okay. But then, right, you can integrate to the inside using divergence, and this is integral over the inside of Laplacian u, which is the delta function at p, right? This is like delta p. So I mean up to a factor. So this is 1. Okay. So this thing is constant as s varies. Okay, so this seems very good, right? So we seem like you seem like you should already, be quite happy because, well, the sharp thing, the best we could hope for is to prove s squared. We've already proved s, right? Not bad. So it turns out that now you get very excited. You go back, you start plugging in every phi that you can find. You're just plugging in random phis, but nothing works, right? It's not good enough. So this is not a good enough decay. Okay. And so it turns out that it seems like you need to upgrade to, maybe there's a different path here, right? You never say you have to do something, but it seems like you should upgrade to s squared. Okay. And in fact, if you can upgrade to s squared, you're done. Okay, so let me show you just briefly why this is true. So if remember that f of s is the integral over gamma s of grad u squared, and gamma s is u equals s. Okay, and so if you've done that, you're actually done, because if you have a function which satisfies this bound where this f of s is O of s squared, forget about the function being harmonic. You can conclude that you're flat. So the first point is Shane, Simon, Yao tell you that the stability inequality, which is kind of an L2 based inequality, you can soup it up to an L3 based inequality. Right? This is they have a sort of like an upgrading trick. And so then you should use, again, right? See, we're always using u as the coordinate. So you should think of u as the radial coordinate. We want to take a cutoff function that depends on u only. Okay. Right? So you get this. This is just verbatim. But now I want to use again, coarea is key here, right? So I give up a power of this and I integrate over the level sets, right? So, right, but this is precisely f of s, okay? So then I get this. But if I know that this is O of s squared, then this is like integral 0 to infinity phi prime of s cubed s squared ds. But this is like, grad u cubed on R3, or not grad u, like w on R3, right? Because this is precisely the R3 area form. And this is a thing you can make go to 0 using the log cutoff trick. Exactly like you can make grad w squared go to 0 on R2. Okay, right? So this is the critical norm in that problem. So you use the log cutoff trick exactly like you would on R2, and it just works. It actually even works better. You get a little bit faster decay. Okay, is that okay? So the moral is we have O of s. We have this quantity f of s, right? So f of s is integral gamma s grad u squared. We know O of s, and we want to get up to O of s squared. It's kind of it seems quite simple, but we were very stuck here. And so then miraculously, you work and work, and miraculously someone saves you. And so this paper appeared on the archive as we were working on this problem. So Mutiano and Wang, and I really like this paper. And so they were studying, again, you have to remember this is a scalar curvature problem, like I said in the beginning. And so they were studying, and again, I forgot, of course. So suppose you have a 3-manifold with non-negative scalar curvature, and it's non-parabolic, so that means there exists a green function, as I now know. And so assume that it has compact connected level sets. That's great, because that's exactly our situation. Then exactly this quantity f of s satisfies an ODE, right? This is amazing, right? We're super happy. Okay, so this is the ODE. Okay, so on R3, remember that what f of s is 4 pi s squared. So, well, you can see that obviously on R3 you get 0. Right? Even the thing inside is 0. But in general, okay, so then you see when I saw this, I was very excited. Because of the following game. So suppose you have this inequality, and Mutiano and Wang explain this. So you could integrate from like s naught to s minus 1 f of s minus 4 pi s prime. So this integral ds is less than 0. This is equal to s minus 1 f of s minus 4 pi s minus the thing at s naught less than or equal to 0. And so then suppose you could send S naught to 0. Then if f of s is little o of s as s goes to 0, then this term goes to 0. This term definitely goes to 0. So then you get 0. So that would tell you that s inverse f minus 4 pi s is less than or equal to 0, which means that f is less than or equal to 4 pi s squared. So then we win, right? We throw a party. Okay, but so there's a few dangers, and I think I'm kind of running out of time, so I won't explain exactly. So we only know big O of s. So that's actually quite dangerous. And in order to make this argument work, you need little O of s. Okay. Actually, if you think about it, if you know big O of s, the only thing you can prove with this argument is big O of s back. Right? That's very frustrating. But okay. So that turns out that you can play a game and regularize. You can prove a slightly different inequality that works out. It's kind of technical, but it just works once you see that you could do it. It's a bit complicated. I'm not going to discuss it. But since I have only limited time, the real problem is this. So again, I told you that this minimal surface does not have non-negative scalar curvature. Right? So in fact, scalar curvature becomes a bad thing, right? We have non-positive scalar curvature. So whenever you prove an inequality where you assume something is non-negative, if it's not that condition, it probably becomes a bad term in your inequality. Okay. So, all right, fine. I'll skip that. So because you don't have this, you get a bad term. Okay. So you have to regularize the Mitiano and Wang argument. And then, so like this is the thing you would get from Mitiano and Wang if you knew that you had non-negative scalar curvature. But this is what we get here. Okay. And so A of s, remember, is integral over gamma s of the second fundamental form of sigma squared, because this is minus scalar curvature. Okay. So you get this. All right. So I definitely don't have time to explain that proof, but this is what comes out. And so just in my last few seconds, you have the following two inequalities, right? So this is what I explained at the beginning. You have the Stern-Bochner formula and the stability inequality. And you also have this thing coming from the idea of Mitiano and Wang, and you get the following inequality. But now, right, if you're an analyst, you should be very happy because now these inequalities are fighting, right? So the first one bounds f by a, the second one bounds a by f. Right? So that's awesome because now we should try to put them together and see what happens. Okay. So the nice thing is, so suppose we want to prove that this is true, then we need to control these terms. Okay. But these terms, well, we can choose phi precisely so that this phi becomes this term. Okay. So let me just draw a picture of phi. Okay. So you choose phi to be, okay, like let's factor out like we're gonna have overall factor of t, but we put that back in at the end. So if you choose phi to be constant up until time t, so phi is a function of s, right? And so then it decreases. Okay, and then you do some cutoff, but S large is easy because that's the pole. We understand everything near the pole. This is the dangerous region. Okay? And so the nice thing is actually the log cutoff trick saves you again here in this term. I don't have time to explain exactly how that works, but log cutoff allows you to plug in such a, because right, this is not, it should be compactly supported away from 0, but it's not, so we have to cut off again. And so since I'm running out of time, what you get is the following, right? So what I've shown you is precisely how to estimate this term in terms of some other stuff. Notice that f of s comes up again in the estimate. So we put this here, we get an estimate for f. Well, it's going to depend on f again, right? This is the estimate. But now, okay, I'll just, this is a nice little analysis exercise. You have such an inequality. This inequality is very good because f is controlled by f, but only at earlier times, right? Like going to 0 is hard, right? But you don't estimate things on smaller t, only on bigger t. And so because the 1/3 is less than 1, right? You can think of this as an estimate like f is less than t squared plus 1/3 f, right? And you can absorb this here, okay? I mean, if the integral was a pointwise thing. So actually, it's a little bit more tricky, but not much. I mean, basically that's the idea, right? And so then you get this and you're done. Okay. So I'll stop here and thank you very much, but I'm glad to take any questions.